All right, we are recording. Everyone's here. Good. Okay, cool. You can see my screen?
Yep.
Cool. Okay, let's get started then. So we're going to talk about ABCI. At the last one, actually, we talked about the peer-to-peer connection, but we forgot to record it. So please, anytime we do dev sessions, remind me to record in case I may not be, because I think the last one was a pretty good one. But so this time, we'll talk about the ABCI stuff. So, there's obviously the ABCI package in here. It's got a README that kind of explains a bunch of what's going on. Most of the details are actually in the Tendermint docs site, which are reasonably extensive. But here we're going to talk a little bit more about some of the implementation details and how the client and server works and how we use it in Tendermint. So I guess we'll start from the top, basically in the node. And the main way that Tendermint actually interfaces with the ABCI stuff is through this proxy package. And the proxy package, it's called proxy because it's basically a proxy to the app. So you see this proxy app terminology around. Basically, this is like our, maybe it's a wrong term, but we also use it at the command line level when we go proxy app equals KV store. So basically, the proxy app is referring to this proxy package and to how we interface with the ABCI client. So in typical Tendermint use, we establish an ABCI connection with the application where Tendermint acts as the client and the application acts as the server. So Tendermint dials out. And so if you just start Tendermint without anything here, you'll see it dialing, trying to connect to on the ABCI socket. So if we go back into the node and we look at where the proxy is used, so the thing the node keeps is this thing called AppCons. And so if we go look at that, it's basically an interface. It's a service like all things that can be started in Tendermint. And then it supports these three connections, which are basically the three independent connections that Tendermint opens with the ABCI application: the mempool connection, the consensus connection, and the query connection. And it sends different messages along each one. So this interface actually returns, each of these methods returns its own interface that restricts the kinds of functionality or the kinds of messages that Tendermint can send on those connections, so that in the, at compile time, we can check that we don't say send a commit message on the mempool connection or a deliver TX on the query and so on. So if we look at AppCon mempool, for instance, the main thing it has is this check TX async. We'll talk about all this stuff in detail, but just kind of showing at a high level. Consensus connection, init chain, and then all the block delivery stuff. And then the query connection is querying and info. Okay, let's go back to here. So when we create a new node, we pass in this thing called a ClientCreator, and this is basically also an interface that returns a new ABCI client. So this is something that folks can pass in to kind of abstract away all the details about how Tendermint connects to the application, and this is where the various implementations can actually be dependency injected into the Tendermint node, so that it can either connect over gRPC or over a local function calls if it's running in process, or over the ABCI kind of standard binary streaming protocol. And then when we actually go to set things up, we create one of these new AppCons that implements that interface that returns the three different types of connections using that ClientCreator, and then we can actually go start it. And then the proxy app gets passed in to the handshake, and and then the pieces it needs are passed in to the various componentry. So the mempool only gets the mempool connection from the proxy app. The block executor only gets the consensus connection because it doesn't need to send messages on the mempool or anywhere else. And that's basically it. So if we go back to looking at, I guess, starting with what this constructor does, it's just a very simple, it wraps this this. So the new AppCons, which implements this interface, we have this MultiAppCon struct that's down here that implements it, and it's just very simply holds implementations of each of these connection types, and then also the client creator. And the reason we have this client creator is so that we can actually create multiple connections all at once using the same style of connectivity to set up actually independent connections. So if we look at the on start for this thing, basically, so this is the on start for the MultiAppCon, which is the thing that got set up from the node and started. And so it's going to go and create the 3 independent connections, all using the same underlying client creator. So the client creator that got passed in is either going to set us up for a local client, or the ABCI binary client, or the gRPC client. We can look at that in a second. And then each one, we call this new ABCI client to actually give us the new connection, right? And so now here we have so now that we have a new connection, then we actually go and enforce the type on it. So now we're saying, okay, this is going to be purely a query connection, so that the only kind of messages we can send over this full ABCI client is going to be query messages. And then we do the same thing for the mempool here, and then the same thing for the consensus, and then that's it.
Is this not some extra overhead? Because that's 3 fully independent connections, whereas when using sockets, you can reuse the same connection.
Mm-hmm. It is definitely extra overhead. I don't think it's particularly significant. I mean, I don't have benchmarks or evidence of that, but the reason we wanted to have these 3 connections is because we want messages to be able to come over them concurrently. And we want to kind of simplify logic on the application side and on the server side so that it knows which application state messages coming over the connection correspond to. So when we, can you guys see the browser now?
No.
Oh. How do maybe I just go here. How about now?
Yes.
Okay. So in the ABCI docs over here, we talk about applications, we talk about state, and how basically we expect that a typical application, and this is for instance what's done in the SDK and others, each application maintains an independent state for each of these connections so that they can all be read and written to concurrently, and that a message coming over a particular connection informs which state it applies to. So it's a little bit extra overhead in terms of the connections, but we're expecting these are all local connections anyways, and it should simplify on the application side knowing which state it applies to.
Okay, I wonder if for pure sockets, it may make more sense to have them as one, since TCP will handle multiplexing. But I also think no one should use pure sockets, and they should be using Unix domain sockets.
Right.
So not worth changing the code for.
Right. So I think this is probably how we want to do it, unless there's really, the logical separation is really helpful. It also makes the code cleaner on all sides, and it's probably not enough of a performance concern to really matter. Okay, so if we get back to this, if we look at, let's go back to the node and let's look at this client creator. So this new node function takes in a client creator, but if we look at the default one, default new node. Here it is. We can see the client creator that it passes in is this default client creator that we have in the proxy package. So if we go look at that thing, here's all the magic. So now, this is where we're seeing the KV store that you might pass in through the command line, where basically, well, the KV store, it used to be called the dummy, but we retired that name because it's a bad name. We should actually probably remove it outright. It creates a new local client versus if you don't pass one of these hard-coded application names, then we actually fall back to the remote client. And so the local client basically means this thing is running in process and it's passing in a hard-coded application, right? Whereas the remote client means it's going to communicate over some address with some transport, whoever that is. I think it might be Zarko. Hey Zarko, I'm gonna mute you. Address and transport. So, so in the SDK, for instance, we run that in process, but that's not reflected here, right? There's no like Gaia in this. You can't actually start Gaia from here. So basically on the SDK side, when it calls new node, it has to pass in its own client creator that is a new local client creator that uses the Gaia app. So if we go here, new local client creator, sorry, I don't know exactly where it is. It's in server start. So now we're in SDK. This is where we set up actually Gaia. And when we call new node, we pass in the new local client creator with whatever app we've set up in process here. And so, there's a bunch more logic. We don't have to dive too deep into the code here, but basically, this is where the in-process Gaia app is being set up, and then here's where it's being actually passed into Tendermint using that local client creator. So if we go back here, oops, and let's go back. Right, sorry. What? Oh. Yeah. Okay, so the new node, there's all kinds of other things that get injected in here. We don't have to talk about those. Really, we're just looking at this, the default client creator. So then we have the local client and the remote client. So here's the local one, very simple. Notice it has this mutex, and then it has an actual ABCI application. And this types here is actually the ABCI types, which is a little bit confusing because we also have Tendermint types. So this mutex, where does it get used? This mutex it gets passed into the local client, right? And so this basically, because it's a local client, and so it's running in process, this mutex is actually held by each of the connections. And so in the in process case, the messages actually can't run concurrently; they run one at a time. And I believe this is what led to a recent deadlock issue where the mempool, the checktx in some application panicked, and it caused the consensus to hang because of this mutex basically wasn't getting released. So in the local client, this mutex is being shared across all of the connections, and is what's passed. The same mutex is being passed in to each new ABCI connection. So to the query one, the mempool one, and to the consensus one, they're all using the same thing. Whereas in the remote client, we don't have that. We're setting up 3 independent connections that are being connected to some external process. Yep.
I might be missing something silly, but why do we need a mutex here?
So the mutex is used basically in this local client, and the reason it's let's see. I can't recall exactly right now why it's being shared across all of these connections.
Even on a single connection, because I'm wondering if we may be able to just remove the mutex via more clever data ownership. Because mutexes are actually a large overhead here, especially when we add defers.
Mm-hmm. Yeah.
Like our previous claims about our fears of, it's not. Yeah, I think it is a significant overhead.
Yeah. I remember doing the, I'm going to look into this further. I can't recall on the spot why we have it, but there is a good reason, and
okay,
I'll dig it up. Obviously, we're missing comments. Explain why. Great. Okay. Yeah. Thanks for pushing on that. Okay. So then if we, so these are basically just, there's a lot in this proxy package that's just about really wrapping the ABCI, the underlying ABCI client ultimately, starting with this MultiAppCon and then going down into this client. And so then if we actually go look at the ABCI stuff, so now here we're in the ABCI directory. Of course, everything is actually defined in types, and then we implement the client and the server. So Tendermint really only uses the client, and the server is what's used by any application, any Go application that's running out of process, right? So if Gaia wanted to run out of process and talk to Tendermint over a socket, it could use this server. But Tendermint itself is really only just using this client. So if we look at the client, we basically have the 3 different client implementations, the local client, the socket client, and the gRPC client. And if we open this client.go, it defines the general interface for all of the ABCI message types. Oops, sorry. And so basically for each ABCI message type, we have both a asynchronous and a synchronous option. And so the idea with the asynchronous option is that you can send messages over the socket and start sending more messages before you wait for the response from the original one. But though it's asynchronous in the sense that you're not waiting for responses, the ABCI is designed so that it expects the messages to be ordered, right? And really what these async calls are used for primarily is deliver TX and check TX, so that these transactions can be forwarded to the application asynchronously, so that you can start sending the next transaction before the application finishes processing the ones before it. But when it gets the responses back, it expects them to come back in the correct order. So it's on the application to make sure that the response order is the same as the request order, and yet we can at least send them asynchronously. So the client itself supports all of these, right? Synchronous and asynchronous for everything, but we don't actually use all of these in Tendermint. So if we go back to looking at the proxy app, basically we see for each of these connections, we only use a subset of the total clients, right? Of the client methods. So the consensus connection, the only async one it uses is deliver TX, and then the others are called synchronously. In the mempool connection, the only thing we really use is check TX, and it's called asynchronously. And then in the query connection, we have the info and query methods, and they're just called synchronously. So a lot of this we don't actually use. It's just kind of all here for completeness, and for, when this was written, we weren't really sure exactly, ABCI was kind of invented about 3 years ago now, and so we weren't really sure exactly how it was all going to be used and what use cases people might come up with, and we wanted to enable kind of general applicability, and so we just implemented this full suite. But it turns out in Tendermint we're only using a significant subset of this, and so that's why we don't just use this ABCI client kind of raw as is. We have this wrapper in the proxy package to refine and enforce that we only use exactly what we need, so that people, instead of trying to understand how we use ABCI by looking at this client and seeing all these methods, all they have to do is look at these connection interfaces to see just exactly the methods that we actually do use.
The async calls don't need mutexes, right?
The async calls don't need mutexes. So that's not really defined here. That's more like an implementation level.
Yeah.
In the remote client, there's no mutex. In the local client, async is actually a farce, because it's just a in-process function call. So we actually do wait for it to return. So why don't we just look at that now? So so the other thing we have in the client is this this constructor, so new client, and basically we set up, this is actually to set up a remote client, so we can set up both a socket or gRPC. Sorry, I think before I said transport was TCP or Unix. It's actually socket or gRPC. The TCP or Unix goes in the address, so both, so there's like a matrix of kind of 4 possibilities. Yeah, we'll talk about the request response stuff after. So if we look at the local client here, this is the setup. This is the note about the recent deadlock we had with the mutex and why it needs to be unlocked. And then, so if you look at the asynchronous calls, they all actually, they're actually all synchronous, because if we look at the synchronous calls, all they do is call the, is that right? Oh, no, it's not. It is asynchronous. Looks like I don't always know what I'm talking about. Okay, so the synchronous calls are basically calling the application directly with a direct function call. whereas the async calls are, oh yeah, they're also doing it directly, right? So it is synchronous, yeah. So it just has this extra callback thing to satisfy the request response object, which we'll show you in a second, right? So so for instance, both query async calls the query, which is a function call that's going to return fully, so it's really a synchronous call, and query sync does the same thing. You know, calls the query method on the underlying application. The only difference is this request response object. So whereas the query sync returns the response query, so this is like the other half of the ABCI. So if we look at the actual ABCI definition, it looks like this. And this is what's basically defined in the documentation and in the protobuf file. This is just a nice Golang version. So for each method, you know, here there's no notion of synchronous or asynchronous. It's just, you know, request response. So that all the async stuff is really just an implementation detail. And then for each one, we have a request and a response for them with all the fields defined in the protobuf file.
Sorry, could you repeat the sync async thing again? I didn't understand why it's not in the proto file.
It's not in the proto file because it's an implementation detail. So in the proto file and in this application interface, all we're doing is defining the message types, which are the request and response, right? So when you go and implement your application, you don't have to worry about anything about synchronous, asynchronous. All you do is implement something that satisfies this interface, right? So something that has all of these methods and that takes the request and the response.
Oh, I see. Okay.
Right. So if we look at like the KV store, for instance, so here's the KV store, and you know, here it is going and implementing the actual ABCI application interface. It's got an info, request response. It's got deliver TX, request response. Commit doesn't take any request, just response, query, request response, etc. Right. So when you're actually just implementing the app, you don't have to worry about async, sync, or transports or anything. You just implement something that satisfies this interface with all these message types defined in the protobuf file, right? But then in the actual implementation, we have a lot more about synchronous and asynchronous calls and handles for dealing with that.
In the in-process case, why can't the async calls just be like green or go threads, go routines?
They could be. It's just not really. It would just be extra complexity for likely little gain. So we could do that. We probably could make it actually asynchronous, and you know, that would be truer to the story of, well, you can send the next transaction before the last one was processed. So it is kind of a little bit of a farce, to be honest. But the thinking was with the asynchronous calls that really you're waiting for. You know, you're communicating over a socket, and this thing needs to kind of be sent and then processed on the other side and sent back. And most applications are probably going to be doing that, and some of them might be slower. And there's all kinds of serialization that has to be done on both sides, so that there's going to be more overhead in that case than there will be when it's in process, right? Because if it's in process, you already have the structs in memory. You're just you can be passing pointers along and so on. So there's less overhead, right?
It sounds like this was written with this idea that most state machines won't be using parallelism, which I think is false, because I think we would expect almost every state machine to have parallel signature verification.
Yeah, so this was written in late 2015. So, you know, Ethereum had just launched, kind of thing, right? and it was very much motivated by learnings we had from re-implementing the Ethereum virtual machine and trying to think about building applications on Tendermint over 3 years ago, right? So I absolutely agree. At the time, it was very much, well, this is what's going to work for at least a few years, probably 3 to 5 years before we really need any major changes to accommodate, you know, any kind of state machine level optimization. At the time, we were already thinking a little bit about parallelization stuff. It just didn't seem like it was really going to be necessary then. Now you can still support that through this interface just by buffering things on the application side, processing them in parallel, and making sure you return responses in the same order. But you know, that does add you know, additional complexity to the application developer, and it may be that we want to start thinking about how the ABCI interface can be improved to support these concurrent processing of transactions and signature aggregation and all this kind of all these optimizations we've started talking about.
Cool. Thanks for the context.
Yep, no problem. Cool. So that's the application interface, and then so it's important to distinguish, and it can be a little bit confusing. So this, let me just zoom up a little bit. So here I'm in the ABCI package. In the types folder, we have all of the protobuf definition file, right? So this is where all the requests and responses are actually defined with all their fields, right? And then in this application.go, we've defined a Go interface that uses all of those protobuf generated message types. And this is the thing that a Golang application developer is really implementing, right? So they implement some kind of application struct and they implement all these methods on it. So for instance, in the SDK, Cosmos SDK, in the base app, this is what's being implemented. The ABCI application interface is being implemented by this base app thing, right? And it maintains all this internal state, and then it has all of these functions like begin block and so on, right? Implementing this interface. And so this is what the application developer actually sees. What we're talking about in the client is what Tendermint is actually using as the implementation for potentially communicating over the socket, and that's where all this stuff about synchronous and asynchronous and and this response callback, which we should probably talk about now, come into play. So this is a lot more complexity because of the implementation detail than just the application interface itself. In some sense, the synchronous calls are roughly equivalent to the application interface, except they also have these errors. And you'll notice, and this was actually quite conscious and a little bit contentious, that none of these, in the application interface, none of the methods return an error, right? And the idea there is that basically any error that might get returned is actually some kind of implementation detail and is somehow fatal, and there's nothing we can really do with it. So the application might as well panic, and we should catch that. Now we probably need to build a little bit more infrastructure around that and actually like catching those panics properly. And as we've seen, we've already had some issues around them. But if something actually encounters some kind of recoverable error, that's supposed to be captured within the error code that you see in some of these response objects. So the response query, for instance, has this error code, and so does the response deliver TX, and same with check TX, and so on. And so this is all summarized in the documentation somewhere, I promise, over here, right? So right at the top of the methods and types, it basically talks about this, that most of these don't return errors because an error would indicate a critical failure, and there's nothing Tendermint can do. So basically the problem needs to be addressed and everything needs to be restarted. Whereas all these other methods, these four in particular, return application-specific response codes, some of which could be errors. And of course, now we have this code space string, which is introduced recently to help namespace the different possible application-level errors. So that's in the application interface. There's no errors, but then if you look at the client implementation, all of these things have an error because now the error refers to an actual error with at the implementation level with the communication over the socket, and this is something that programmatically we might want to be able to handle in some way or another, but we don't bubble this back up through the application interface. We have to deal with it somehow, right? So this stuff is all basically wrapped by that application interface, which hides any errors, because at that level there's really nothing we can do, and so we don't want users to be thinking when they're implementing their application, in that commit sync that commit should somehow be able to return an error if something goes wrong, because it shouldn't. Whereas the server itself can if there's some kind of error in the communication. Does that make sense? People get what I'm kind of saying there?
Just one question. It's a bit unrelated. For a Golang application, Tendermint application, is there any benefit of using the socket API or socket client instead of InProcess one?
The benefit is that in right now, no. In theory, you could like upgrade the application without restarting Tendermint, but currently we don't actually support that on the Tendermint side.
Until we fix this whole batching and parallelization issue, the local one's gonna be faster just because it can utilize shared memory instead of a socket.
Right. So the question is there any advantage to ever using the out of process one?
Well, currently, there would be because of parallelization gains.
What do you mean?
Because the async stuff in the gRPC case.
Oh, that's right. Because the async stuff is all running sequentially. Yeah, that's a good point. So I wonder though if that's offset by the overhead of the socket connection. That'd be interesting to look at.
Parallelization is, or a single signature verification is around like 200 microseconds. The socket latency is around like 10, between like 1 and 15 microseconds, depending on time. Mm-hmm. So being able to parallelize just one signature more like makes up for it.
Yeah, right. So the fact that the check TX and the deliver TXs can actually be running concurrently would be a performance boost compared to if it's running in process and they have to run one at a time.
Yep.
Yeah. That makes sense. Cool. Yeah, great question and answer. Thanks, guys. So the other thing that potentially, if you want, is you could run them over, you could have like different Unix permissions on the processes, for instance, and they could be running on different machines. So there's certain like security and isolation things you could do a little bit differently. You know, the Tendermint process is going to be exposed to the internet because it's talking to peers, whereas the application process doesn't have to be. So if it's all bundled in, it means that your application is part of a process that's also exposed over the internet. Whereas if it's not, then it's not, right? So there's some trade-offs there as well.
I have a question.
Yep.
For the Go client case, why do we have the Tendermint side have the defer? Why not have the app catch panics?
What do you mean?
So if we go back to like the check TX async for gRPC, mm-hmm. we have this defer mutex because the problem we originally had was that when we didn't have the defer there, or the app could panic and then we'd just like crash something.
Mm-hmm.
Or we deadlock. But shouldn't for the Go client case, I feel like the app should catch its own panics.
Oh, sure.
But you need anyway to catch a panic at a Tendermint level because you can't rely on app for doing this.
Right.
In the Go client case, you should be able to, right?
Well, not if, I mean, we don't control the application. So the application could be written and not catch its panics.
I mean, but that's part of the specification. Like we can specify the contract of a check TX async in
Sure.
the gRPC case is you catch your own panic.
In the gRPC case, we're talking about the local client, not gRPC.
Sorry, yeah, local client. My bad.
Yeah. Yeah, that's a good point. And this is what you know. Anton was raising this point when we were running into this issue. He was like, "What is the this behavior is undefined. The application panicked, and it's not really defined anywhere in the documentation or the specification that the application can't panic on check TX." So we resolved it, but technically you're right that we should say that the application should catch its own panic in check TX. But even still, I mean, we can still write Tendermint defensively to be able to catch that.
But slows it down.
I get that you want to eliminate the defer because you're a speed hound, whatever those people that with performance are called. Yeah, fair enough. So we could consider doing that if we make it clear in the specification. But I think for now it's
But even then, I think that like application could just fail to do this, and it's somehow bad practice that the infrastructure code we are not being defensive.
Yeah, I think it's good to be defensive. Yeah, for sure. Okay, so let's talk about let's actually look at how this thing is used, for instance, in the mempool. Because that's kind of a complicated use case. And then...
So, Bucky, just one question before we proceed. So basically, when we talk about synchronous versus asynchronous, there is a client side and also the server. I guess the the complexity is also at the server side or application side is as part of the server thing.
Okay. Yeah. So if we look at the server, now the server doesn't even have the server doesn't even have an interface because Tendermint doesn't actually use it. It's just something that you know, if you're building an application and you want it to run out of process, you would import the server and run it. But the server is basically, you know, as a server is kind of written to support asynchrony kind of natively. And so if we go down to so if you look at the on start, it spawns this accept connections routine, which is basically just to accept the connections. And then once a connection is added, then it has these two go routines for handling requests and responses, right? So when a request comes in, you know, it's a big loop. It's kind of like what we were seeing last time on the P2P layer. Reads the message off the connection and handles the request. And basically the handle request, you know, for each message type, it does something and either calls the application and if it needs to or not. So for instance, response echo just echoes the result back, whereas everything else, you know, if you get a request info, it calls info on the application and then returns the response and passes it over this response channel. So this response channel is like an internal thing for buffering all the responses, and then handle responses is, you know, loops over that response channel, reading messages off of it, and then writing them back out. So the response channel, the server doesn't really differentiate between the synchronous and asynchronous requests. That's really just on the client side on whether or not it waits for the response to come back right away. Or the server is kind of written to support asynchrony, and then it's really just up to the client whether or not it waits for a response in terms of asynchronous versus synchronous sends. Does that make sense?
Mm-hmm. Thanks.
Yeah. So the server implementation is relatively simple. It's 200 lines here. A huge chunk of it is really just this big switch case statement over all the different types. And yeah, that's really it. And the gRPC server too. It's also very, very simple because gRPC really does all the work. All we had to do is implement on start. Okay, so going to the mempool. Okay, so when we make the mempool, we pass in the mempool connection. So we talked about that. That's the proxy app thing. And of course, that really only lets us have checktx async. And then, so there's these other methods in here, and we'll talk about these as we see them in the mempool. It's the best way, I guess, to understand them. And so this proxy AppCon, where is it used? Oops. Oh. Proxy AppCon. So first of all, set response callback. So this is to support these asynchronous calls, so that when we send a call, an asynchronous call, there's a callback function that gets triggered to deal with the response, right? And so this is a method that's defined only on the connections that need to handle asynchronous requests. So the query connection doesn't do any asynchronous requests, so we don't have the response callback here, whereas the mempool and consensus connection do, so we do have the response callback. And so in this case, for instance, the response callback is this rescb method here, and we look at what it does. It takes a request and a response, and it does a bunch of stuff to handle them, right? So this is in the mempool, where basically it reads out the response and it looks at the transaction, you know, and it checks, is it valid or not? You know, did it return a code 0 or not? And if so, it'll add it to the mempool. Otherwise, it rejects it and it ignores all other messages. Now, it occurs to me that this may not actually be checking that the order is correct. And so a bad server implementation or a bad application might actually be able to return things out of order. And so that's worth looking at further.
Just regarding the ordering, I was wondering why we just don't add for each transaction a sequence number, and so then it's somehow more explicit, this ordering within a block.
Well,
this doesn't apply, but
this isn't in a block. Yeah, exactly. So in the deliver TX case, I think, let's see. So here's the response callback. This guy, yeah, it's basically the same thing. So again, I'm not sure. So it expects the things to come in order, but it looks like we're not actually enforcing that over here. We may be enforcing that in the client itself. So if we go back into the ABCI client and we look at, so here's this response callback thing. And so for instance, if we look at CheckTX async, so it calls CheckTX and then it calls this, this callback, and no, so I don't think it actually does enforce that the order is correct, because yeah, there's no like index or anything that it's using to track that.
But you don't need to, because in the mempools like callback thing, you're grabbing the TX from the request object.
Right. So in the mempool here, oops, res CB. So it grabs the transaction out of the request, and yeah, that's right. So in the mempool, it's okay, but it could still mess up the ordering, right? If they were supposed to be processed in a certain order, but the responses come back in the wrong order, then that could cause the proposer to propose a block that has transactions that are, you know, in the wrong order.
No, here, like, I'm not sure here that it's still fine, because you get transaction from a request, but response is what, like, you got some response. You are not sure if this response is really a response for that particular request.
We do know that because the request is embodied in the response. Like, you don't just see the response, you see the request and the response.
Yeah, but do we check? That's the thing. I'm not sure we check.
Yeah, that's what I'm saying. I think we might not.
Sure wait, the question is, just make sure I understand your concerns, like that the request and response don't match up.
Is it?
That's guaranteed, right?
By a proper implementation.
Yeah, but this is we don't check this. We don't.
Oh, I see. Now I see the problem. Okay, right. So we need to have the response we need to be able to get the transaction either sequence or data from the response object.
Yeah, but like with sequence number, it's trivial.
Yeah.
Unless we mess up with sequence number, but then this is a different story. But then also this thing, when you are sending asynchronously, then it's also easier from the application to. It doesn't need to pre-order it before sending it back. It can just send it back and then you look at the sequence number. So.
Right. So right now it's basically just given to the server implementation to get this right, and you know we assume this is done correctly, and so there's no problem. We could consider enforcing it on the Tendermint side, which would allow us to catch a bad server implementation. But it's not really. The
reason why I think that if it's not too costly to be defensive, we should probably be, because I remember Marco from IBM was saying that they are having tons of issues where basically the people developing using their software are having a lot of issues, and they were kind of blaming them for this. So they even introduce all those relatively complex approach for like executing transactions before agreeing, so they can deal with non-deterministic code. Because before, when it was supposed to be deterministic, people were just, I don't know, you can say it's bad coding, but if the library can still tell you immediately this is a problem, then I think also from developer point of view, it's a nice feature.
No, I agree. So it's a question of, it's not something that application developers have to worry about. It's more the people that actually implement the ABCI server, right?
Exactly.
And so, we could build, and we probably should build some kind of like testing suite so that when someone submits or when someone builds an ABCI server implementation, we can actually like test it out and look for any cases where maybe things come back in the wrong order, and then, and then they know. Whether or not it should be built into Tendermint, it could be, and it might not be a bad idea, but so we could open an issue for it, but it doesn't seem like particularly high priority right now.
Yeah, but this ABCI server is this server, what you were showing us. When you say ABCI server, it's okay. And so we don't see this server as kind of part of the Tendermint or responsibility.
Correct.
Okay.
What's up, Dave?
I'm more of a fan of the testing case, but if we did want to assert it in the Tendermint side, we could. It's pretty cheap to just add a counter to the request and the response.
Yep. Yeah, it wouldn't be that bad. Yeah. But I think we want a test suite anyways for these servers so that people can submit them, and we can reward people for building a good ABCI server that like passes all our tests, or at least we have some like test vectors or some kind of standard harness for everyone to know that they built a legit ABCI server that's going to work. And that way they don't have to like run Tendermint for a while before finding out that there's an issue, right? So.
And then we don't slow down our high speed case.
And then we don't slow things down. Yeah, exactly. Yeah. So, okay, I think we need to wrap up soon, but so this is basically the idea. So then when we actually come to the checktx method in the mempool, it goes and after a bunch of initial stuff, it checks if there's an error, if there was an error in the underlying connection first. So because this is synchronous, an error would come back, or sorry, because it's an asynchronous call, any error would come back asynchronously. And then it calls the checktx async, and that's kind of it. We'll talk about this callback in a second. So then when the thing in the underlying ABCI client, when the response comes back, it will actually go and trigger that res callback we were just looking at, and that's when that'll run kind of in the background. And that was set because of that proxy app. So if we go look at that again, say in the local client, we set the what was it called? Set response callback. So that was set here. So that then when we actually call checktx async, we call it on the application, and then we call this this callback method, which calls the whatever the response callback was set to, and then returns this request response object, which contains both the request and the response. And that way, and then that will so this callback will trigger that res CB in the mempool. And then this request response object is kind of left over and given back to the mempool if we want to do anything else with it. And so we actually do something else with it. And that is async. We potentially set another callback. So what's that about? Well, when we call checktx, we have the option to pass in another callback. And basically that is used in the RPC. So if we look at where checktx is called, it's called in two places. One is in the reactor, when we actually receive a transaction from a peer at the mempool level, we call checktx, and in that case, the callback we pass in is nil. So we don't do anything with the request response object that got returned. But in the RPC case, when we do broadcast tx sync or broadcast tx commit, we do pass in a callback, right? So here is calling checktx, and then here's this callback function we're passing in, so that basically we know the difference between these broadcast methods ultimately comes down to this callback that gets passed in. So in this broadcast tx async, we just pass it into the checktx, and then we're done. We don't even wait for the checktx to finish processing. Whereas here, we do wait for the checktx to finish processing, and the way we do that is with this callback function that blocks waiting for the checktx response to have actually completed. So this response thing that comes in here right, is what we're then is what we're waiting for with this response channel, right? So we ultimately wait on that channel until that call. So this, you know, this is going to block until this callback function has actually executed and went down to checkTX. Once we called the checkTX async, we get this request response object back, and then we set a callback on it. So this is a request specific callback compared to the other callback that was a kind of connection general callback. So for every request, the other callback was getting called, whereas here it's just specific to that request, because it's like, okay, this came in specifically over the RPC and we want to wait for it to complete. And when it completes, call this callback, which is going to unblock the rest of the RPC functionality, right? And so if we look at this set callback thing, it's defined on this request response object, and it basically, it just sets this callback thing underneath it. And the important thing here is that when we then go to, for instance, local client, and we look at the callback method, well, in this case, it actually goes set done right away, which should trigger the, oh, so in the local case, the local case isn't actually asynchronous. So this all happens right away. So by the time we set callback from the mempool, this done has already been set. And so then we actually call it right away. So that all kind of happens synchronously, and it's a little bit of a hack. But in the socket client, for instance, when we look at checkTX async, socket client is much more complicated. We actually didn't have a chance to look at it, and I think we need to wrap this up. But so we create this request response, we pass it over this request queue, and then we read things off the request queue. And oh no, that's in the flush queue case. Sorry, 1 second. Here we read things over the request queue. We say we're gonna we say that they're gonna send, and then when we receive the response, that's when we actually go and call. That's when we actually go and call done. So here actually, so this is in the socket client. We actually, here's where we're actually checking that the request matches. Oh, did it just exit? Hello?
No, we're still here.
Oh, sorry. So sorry, I'm kind of going through this quickly now, but in the socket client, this is where it actually checks that the request matches the response. Mm-hmm. So it looks like we are actually checking that here. In the local client, we're not, but the local client is synchronous anyway, so it doesn't matter. Whereas here, we're actually doing it, and then we call done, and so then we check if there's a callback, and if so, then we actually call that callback, and that would then, for instance, unblock the RPC method, and we'd be able to continue on.
I think we may need to rethink the mempool mutex structure, because right now, if in the local client case, when you have checkTX, like you have a mutex, and it's not going to, the mutex is going to stay locked until the callback is complete. Mm-hmm. And so what happens if I give you like 1,000 different checkTXs, and then a new block comes in, so you need to call update, and you need to call reap, because you're the next proposer. You might have to wait for these 1,000 checkTXs to complete before you can update, and then you have to wait for that to complete before you can reap again. Which,
but the 1,000 checkTXs run one at a time. We don't hold the mutex across all of them. So the update would get a chance to run before they all complete, no?
There's no priority in mutexes, so it's like random.
It's random, yeah, that's right.
So
yeah.
We can expect it to be like 1 out of 5 after 500 different things, because it's going to be 1 out of 1,002.
Sure. So if we want to prioritize the update, then we might need to do something differently. Yeah.
Bucky, can I grab you for the launch weekly too?
Yep. I got to jump off, guys. This was fun. Obviously, sorry I could have prepared a bit better, but I think glad we got to go through this. And let me know if there's any additional questions. We probably should do some follow-up, and there's definitely improvements that can be made. But Thanks for joining and for your attention and all the great questions.
Thanks.
Thank you.
So,
Cool.
Should we talk about the
Thanks,
mempool later? I do think it's kind of important to read.
Yeah, let's do. Should we do a mempool dev session like next week? Do you want to present on it?
Sure.
Awesome. All right. Well, let's schedule that in for next Thursday.
Okay.
Bye-bye.
Cool.
Bye.
Thanks, guys. Bye.